Hi, everyone. Thank you for joining us today. Welcome to Steam Management's webinar series. Today's session dives into the key engineering considerations, common challenges, and benefits associated with steam pressure reduction. Leading today's discussion is Chase Bean, our Vice President of Revenue and Engineering. Chase leads Steam Management's engineering team and brings over 18 years of experience in the energy sector, spanning engineering, project management, and business development. You're welcome to ask questions in the chat at any time, and we'll address them during the presentation, but we'll also leave time at the end for a Q&A. The session is also being recorded, so if you need to step away, the recording will be shared after the webinar. Also, to receive your PDH certificate, just email Chase following the webinar at that email, cbean@steammanagement.com. And thanks again for tuning in, and I'll hand it over to Chase to get started.
All right, thanks, Ashley. We are Steam Management. We provide turnkey retrofit projects with a focus on efficiency improvement in steam systems. Our solutions reduce system energy costs, conserve water, and reduce carbon footprint. We serve a variety of markets, mostly anywhere where you will find steam, and we thank you for joining us today. Our learning objectives for the presentation: we're going to understand how steam pressure reduction impacts system performance. We're going to recognize key technical factors to evaluate before lowering the pressure. We're going to identify energy savings contributors, and we're going to review a real-world case study toward the end. As an overview, there are two main approaches to steam pressure reduction for energy savings. One is boiler pressure reduction or high side pressure reduction. This is just lowering the boiler operating pressure. The idea here is that on your high side of the system, high pressure side of the system, you have some room to lower the pressure, and then your PRVs will regulate that pressure down to the usable pressure in the lower pressure systems. There's also targeted system segment reduction. These are not official terms. This is just what I'm calling these two approaches. But targeted system segment reduction would be lowering the PRV set point, or utilizing digital pressure reduction, where you're modulating the pressure in a section of the system based on a demand curve. So a common application for that would be adjusting the system pressure for a heating application based on outside air temperature, say. In this presentation, we're focusing on the boiler pressure reduction and how to approach that and what the savings are. Boiler pressure reduction reduces fuel and water use and carbon emissions. Typical savings, according to the DOE, are about 2 to 8%. This is best suited for oversized boiler systems and saturated steam systems. And I emphasize oversized there because you'll see as we go through this, basically you basically just need extra capacity in a lot of different aspects of the system to give yourself room to reduce that pressure. So the fact that a system might have had reduced load over the years, it helps for the ability to reduce the pressure of the system. And this approach is an engineered approach. It needs to be carefully evaluated and tested to avoid operating and reliability issues. We'll go through the energy savings components. So the system losses that are impacted, we'll go through each of these in more detail in the following slides, but some of the system losses that are impacted are combustion losses, boiler radiation losses, boiler blowdown loss, the enthalpy savings effect for high pressure steam use, high pressure radiation loss for steam and piping components, high pressure steam leaks from piping components and through PRVs, high pressure steam trap leaks, steam supplied to the deaerator, and your boiler feed water pump electricity is reduced, can be reduced. So talking about boiler combustion loss and fuel reduction, in principle, operating at a lower saturation temperature can allow a higher differential temperature between the boiler water and the flue gas. So that provides a gain in thermal efficiency. It's not easily quantified without manufacturer data, but it should provide some efficiency improvement. The reduction in energy required to produce the same steam output at the lower pressure also results in fuel reduction, which we'll talk about more in a minute. Boiler radiation losses. Here we're talking about the heat loss off of the body of the boiler. The equations here basically are to convey, the heat losses from the surface of the boiler driven by radiation losses and convective losses. Those are both driven by the temperature differential between the boiler water and ambient, and reducing boiler pressure reduces that differential. Boiler blowdown losses. So here we're talking about surface and continuous blowdown. I've talked about this in some other presentations, but basically surface blowdown is water that is intentionally rejected from the boiler to remove impurities from the boiler. So you have all these total dissolved solids or dissolved solids in the boiler water. They accumulate at the surface of the boiler and they're rejected down the drain. So this is water that's heated all the way up to saturation, and then that energy is lost down the drain, as well as that water. Reducing boiler pressure doesn't necessarily reduce the amount of blowdown from a mass perspective, but it reduces the BTUs per pound of the boiler water, and therefore you're rejecting less heat through your blowdown. If the energy from the blowdown is being recovered through a blowdown heat recovery system, there will be virtually no savings or minimal savings by reducing boiler pressure. One thing to note here too is actually, when you send blowdown to a bottom blowdown tank, there is typically a tempering water valve to cool that water off before it goes to drain. If you reduce your boiler pressure, you actually reduce the amount of steam that flashes off of that blowdown flow in your flash tank. So you're actually increasing the amount of liquid going to drain, and you will slightly increase your tempering water. It's not a significant amount typically, but an interesting impact. As far as the enthalpy savings effect, basically as you lower the pressure of your boiler, you're going to lower the amount of enthalpy that the BTU content that every pound of steam has. And so the amount of energy required to generate the steam is less. So here, this is like a 20 pounds steam. You're below 1200 here. And when you get up to 365 pound steam, for instance, you're well above. One interesting thing to note about steam also at higher pressure. So basically the usable energy of steam is the latent energy that's going from steam to liquid. So when you go through a steam heat exchanger, you're going from here to here. So for higher pressure steam, you actually have less energy that's captured per pound, but then you have a higher temperature, and that encourages more heat transfer. So you probably will struggle to hit the same capacity at a lower pressure, but you actually get more energy per pound out of the steam. And this also comes into play that, like, in your distribution losses, if you're at a lower pressure, you have to lose more energy through your pipe walls, like thermal losses, for that steam to condense into liquid. The enthalpy savings itself is small, but it helps explain why fuel input drops slightly, even if your total steam mass flow stays constant. All of these savings kind of impact each other. Like when you talk about fuel savings, everything that is reduced elsewhere is going to reduce your fuel use. And this is kind of another example of that, where there's other impacts in the system that affect this. High pressure radiation losses for steam piping and components. This is similar to the boiler radiation losses. This is your loss through your pipe walls and your insulation. This is reduced by reducing your pressure, because you're reducing that temperature differential that drives the heat transfer through your system boundary, basically. High pressure steam leaks. So any leaks in your system, you see Keith here pointing at this system leak. Now, if you reduce your pressure, you have less pressure to drive steam through that leak. Leaks are common at piping joints, valves, valve bonnets and stems, and relief valves. They're caused by corrosion, erosion, water hammer, or poor installation or design. And they're driven by, or you can estimate the flow by using Napier's formula for steam flow through a sharp-edged orifice. And kind of the takeaway here is it is that pressure here that's driving the amount of steam loss through a leak. A high pressure steam trap leakage. Poor trap maintenance is a major source of steam loss. A lot of people on this call are aware. This is generally one of the highest payback measures in a steam system is to maintain or repair your steam traps. And I wanted to note that, reducing steam pressure will reduce your losses to the traps, but pressure reduction is not a substitute for proper trap maintenance. Basically, just like in a steam leak, it lowers the differential pressure across the trap. You're lowering the upstream pressure. The downstream pressure is probably the same. And therefore, any traps that are failed open are leaking. You're getting less steam passing through that trap. Accurate savings potential can be evaluated through a steam trap testing survey to catalog all of your traps and their sizes and services, and then the savings can be calculated from there. Napier's equation still applies, but in a steam trap as compared to a steam leak, you're getting two-phase flow through there, so you have to apply a reduction factor to account for that. The condensate flowing through the trap is blocking some of the flow area, so you can't assume that it's all steam. Your steam supplied to the deaerator. This again is when you lower the pressure, it's going to reduce the steam supplied to the deaerator, but this primarily results from the other system loss reductions. So if you increase your condensate return and lower your makeup water demand by conserving energy downstream, reducing your flash steam losses in your collection tanks, reducing your steam leaks and trap leaks, and that all reduces the steam load, which then reduces the load on the deaerator and reduces that steam flow. So it's kind of important not to double count savings. And one of the best ways to ensure doing that is to do a full heat and mass balance and see the impact once everything's balanced out so that you don't count savings in two places, if that makes sense. Reduce feed water pump power is possible. So in a constant speed pump, that's the equation there for pump power in kilowatts. And you can see that this is driven by the differential head or the total developed head of the pump. So if you reduce the downstream pressure requirement, which is basically the pressure acting against the pump from the pressure in the boiler, the upstream pressure stays the same. That would be your DA pressure or your feed water tank height, liquid level height. Then you're reducing the overall power requirement. This can be a problem. This can cause problems in the pumps, which we'll talk about in the next section. But generally speaking, you could reduce your pump power requirement. On a variable speed drive, it's more significant, as we all know, from your pump affinity laws. The power varies with the cube of speed, and the head varies with the square of speed. So in terms of head, your power varies with the differential head ratio to the 3/2 power. So you can get significant savings by being able to turn down your boiler feed water pumps because there's less pressure downstream required. Okay, on to potential issues.
Hey, Chase,
So,
before you go on, we have a question in the chat. It says,
sure.
what is the most cost-effective way to monitor steam traps in real time? such as installing temperature sensors at the inlet and outlet of traps or installing both temp sensors and ultrasonic sensors?
That's a great question, and I don't know if I can answer it specifically. 'Cause it's basically just what is the most cost-effective monitoring solution that is out. And there's all different types, there's all different manufacturers. To your point, there are types of monitors that have basically used differential temperature between the upstream and downstream of the trap. There's also monitors that are basically a clamp-on ultrasonic monitor. I would, we're brand agnostic, so we don't push any particular method, but we do recommend ultrasonic testing as the best method for testing steam traps. And so I tend to think of monitors that are based on ultrasonic technology to be maybe better, but I'm not putting down any of the other solutions. I do know they have their benefits as well. One of those being a lot of the thermal differential monitors are able to power themselves. They generate power from that thermal differential. So there's pros and cons of each. I don't know off the top of my head what is the best price point between the two, but and some of that price is the install and the commissioning of the system and the ongoing monitoring subscription costs. So it's not too easy, but if you are interested in that, that is something that we do, and we could help you implement that type of system. And you can reach out to me about that. So anyway, non-answer, but hopefully that was answered your question a little bit. Okay, so on to potential issues. Again, I'll talk about each one of these in more detail. But some of the issues that can be caused are boiler carryover, boiler water carryover, potential for boiler tube overheating in water tube boilers, increased steam velocity in piping, increased steam pressure drops, failure of steam system PRVs, the need for flow meter recalibration, feed water pump cavitation problems, reduction in steam trap performance, and reduced output power from steam turbines. I see another question here. With the potential issues when the boiler pressure is lowered, do you need to check, or is it a concern at all with the heat output at the terminal units, i.e. radiators? That's a good question. So we'll kind of go through that here. And this presentation is more about reducing the high pressure side of the boiler system. And so the idea is that downstream of the PRVs, the pressure would be maintained. But if you were doing a section, like a reduction in a system section based on outdoor air temperature, yeah, you would need to appropriately size that that control valve curve to respond to outside air temperature, so you're maintaining your heat. But that's something that could be adjusted. If it did cause problems, it could be adjusted to increase your steam pressure at different points. Thanks for that question. And that's one of the concerns here. If you do have any high pressure steam users, that's something that needs to be evaluated. Can they still meet capacity? One of those that we talk about is steam turbines. Anyway, I'll get to that. So yeah, thanks for that question. Okay, so one of the potential issues is boiler carryover, and this one we're talking about fire tube boilers. Fire tube boilers can often operate at varying steam pressures with few negative consequences. So fire tube boilers, basically, you'll have the same model fire tube boiler for a 30-pound system as a 100-pound system sometimes. And there's just a few tweaks that the manufacturers do as far as outlet sizes and all. But basically, what we're concerned about here is carryover. So carryover is when boiler water is entrained in the exiting steam and leaves the boiler, and that is undesirable. Then you're getting poor quality steam or wet steam. Also, a lot of times what that carryover is the foam that develops on the surface level of the boiler. So that foam is actually what's getting picked up and carried out. And so then you're adding dissolve solids to your steam. And so that'll have impacts as far as your system performance. You'll get more condensate in your distribution system. If you were to say be using autoclaves at a hospital, your instruments will start coming out dirty. Instead of having clean steam, cleaning them, they'll have spots on them. So it's there's a lot of consequences from it. It's to be avoided. Carryover is affected by the steam velocity, which is the main thing that we're changing here by lowering pressure. The outlet design of the boiler, the steam space in the boiler, which is why fire tube boilers are conducive to changing pressure, which we'll talk about on the next slide. Total dissolved solids and foaming on the boiler, which I kind of mentioned. Rapid load changes. So if there's sudden changes in the steam exit velocity and the boiler inlet water, the feed water coming in, that can lead to like surges and obviously lead to water getting entrained in the exit steam. And then poor blowdown or chemistry kind of ties into the TDS and foaming. Blowdown is how you get those total dissolved solids out of the boiler, and proper water chemistry also affects that. So existing carryover or poor quality steam issues are a red flag that pressure reduction may not be advised. Maybe those issues are something that you can address, and then maybe you could proceed from there. But if you're already kind of struggling with those issues, you don't want to exacerbate them by lowering the boiler pressure. Issues in water tube boilers. So carryover here. So we mentioned that the steam space in the boiler is one of the things that contributes to carryover. You can see in a fire tube, there's a lot of space here. So you get, as you can imagine, just any water that's maybe bubbling up or flying into the steam space has room to settle back down. Whereas in a steam or in a water tube boiler, the steam space is a lot smaller. And so they may be more susceptible to carry over from reducing pressure. Also, generally speaking, water tube boilers are designed for a certain pressure, which we'll talk about on the next slide. Steam outlet velocities are more of a concern because of that lack of steam space. So water tube boilers are generally designed for a certain pressure because of the, among other things, but one big impact is the boiler water circulation. So if that circulation between the downcomers and the risers in the boilers, that's all driven by the density difference based on the temperature differential inside the boiler water within the boiler. So and if you change the boiler pressure, that significantly changes that circulation, and you would have to run a circulation study to verify that it's appropriate. But basically what happens is you need a certain amount of circulation, like in many heat exchangers, but you need a certain amount of circulation to make sure that your tube walls are cool enough. In boilers, if you picture, steam bubbles forming on the tube walls inside of the boiler tube, the water tubes, if that's not immediately replaced by water, it can lead to what's called steam blanketing, where there's just like a sheet of steam at the tube wall, and that basically insulates the tube wall. It leads to hot spots, and it will lead to premature tube failures, as well as lower boiler performance. But as you can imagine, in a water tube boiler, tube failures are more costly to repair, generally speaking, than in a fire tube boiler. In a fire tube boiler, you pull the end open, you retube the boilers. Is something that is regularly done. In a water tube boiler, it's a whole, it's just more of a project. So I would say, generally speaking, a water tube boiler is not a good candidate for pressure reduction like what we're talking about, although you could still evaluate it if you wanted to. Another effect is increased steam velocity in the piping. So again, I mentioned before, systems that have been, the load's been reduced over time are better candidates for this pressure reduction. And this is one example why. If the system was originally designed for a certain capacity and the pipe sizes are designed for a certain velocity at that capacity, now you've reduced the load, and so you have more room to increase the velocity at the existing load. So when you lower the steam pressure, you lower the steam density. So the same mass flow results in higher velocities. Um, and why is that an issue? It's pipe erosion and noise through the piping, water hammer concerns. So any water in the piping is more susceptible to be picked up by higher velocity steam, which can lead to, high velocity slugs of water traveling down the pipe. That's one form of water hammer, which can be very destructive. Along the same lines, like moisture carryover, so high velocity steam will entrain water, pick up water basically out of drip traps and lead to wet steam issues. And typical velocity limits are shown there. These are, you'll see different limits by different not manufacturers, but different publications. But these are some generic limits. I would say 120 feet per second is kind of on the high side for saturated steam. For the headers. Along the same lines with the higher velocity, that also leads to increased frictional losses or pressure drop through the piping. And so the impact of that is it may further affect the impact of reduced pressure. So if you are looking at, say, the inlet of a PRV and how much pressure is available at that inlet, if you reduce the boiler pressure by a certain amount, you know that you're reducing the PRV inlet by that amount, but then you're also getting additional pressure drop through the piping system from the boiler to the PRV. So instead of a 5-pound drop from boiler to PRV, it might be a 10-pound drop. So that needs to be evaluated. And so that can lead to failure of the steam system PRVs. So you need to make sure, well, first, PRVs are basically pilot operated regulating valves that maintain a stable outlet pressure. So these are located at letdown stations. This is how you go from a high pressure steam system or high pressure piping to your low pressure sections of the system. And their performance basically, it depends on the condition, but also the differential pressure that is available for flow. So if you are maxed out on the PRV capacity at the existing pressure, then you're not going to have any room to reduce that pressure. So again, an oversized system is a better candidate here. If you have a large, I say large inlet swings, I mean large inlet reduction in pressure, it can cause reduced responsiveness and reduced capacity. And so that all needs to be evaluated. The need for flow meter replacement or recalibration. Steam density decreases as the operating pressure is reduced. So for differential pressure meters like an orifice or a venturi, the lower density results in a higher differential signal. So that would be inaccurate. Many meters rely on fixed density assumptions. So for best practice, you would evaluate the existing meters, make sure they're within their design velocities, recalculate or reconfigure the flow meters when the pressure is changed, and then consider a mass or compensated flow meters, especially if you have a system where you intend to vary the pressure up and down, then they will compensate for that, the differences in the steam properties. Feed water pump cavitation problems. So this is a standard pump curve. This is not necessarily a boiler feed water pump curve, but I just pulled a standard curve here to illustrate the concept. But this is the operating point. Your x-axis on the top graph is flow. Your y-axis is head. And so if you were to reduce the boiler pressure, you would, for a constant speed, intermittent feed water pump, you would run your operating point down this curve. Down here on the bottom, you can see this black line is your net positive suction head required. That's the pressure basically upstream of the pump. And so net positive suction head, or a lack of net positive suction head, is one of the main contributors to cavitation in a pump, especially when you're in a steam system. You're operating at basically saturated conditions. So you're very close to boiling. If you don't have enough positive suction head on the upstream of the pump, then the water coming into the pump will experience a slight reduction in pressure and it will boil. And those pockets of gas just result in the pump cavitating and can lead to premature failure. Hard to explain if you don't understand like how pumps work or pump curves, but trying to convey here that, the faster the pump flows, or the faster the pump pumps, the more net positive suction is required. And so the more likely you are to cavitate. So that's what we're evaluating here. On a VFD, this is less of a concern because the VFD will turn the speed down, maintain the same flow, and hopefully not require additional net positive suction head. So two different scenarios. VFDs certainly simplify the equation, also help operate at the best efficiency point of the pump, and and result in more power savings as well. I will say all that to say, if you reduce the boiler pressure on a constant speed pump, you end up out here on the curve. All you really have to do to mitigate that is throttle your outlet valve down to get you back to the best efficiency point. So it's really not that big of an issue if it's addressed properly. Reduction in steam trap performance. So lower steam pressure can reduce the trap discharge capacity and lift head. You should note that decreasing pressure, as we've noted, it reduces your system losses, and so that slightly reduces your trap load because there's less condensate formed in the system. Also, high pressure system traps typically have plenty of pressure available for lift. So what I mean by lift is the height that the trap has to discharge against, the height plus whatever pressure is in the condensate return system. So if you have to get that condensate up, say 20 feet, then you need 10 pounds of pressure to get it up there. If you're reducing the system pressure, then you're obviously reducing that ability to lift that water. This all can result in condensate buildup and increased risk of water hammer. The good news here is that standard drip trap sizing usually will tolerate about 50% pressure reduction. This can all be verified through a trap survey and analysis of manufacturer cut sheets. And most traps are pretty conservatively sized. So if you look at recommended safety factors when you're sizing traps, the lowest safety factor you usually see is 2 times. So the capacity of the trap is 2 times the load. So there's usually going to be some room here. And also, again, this can be affected by the fact that you've lowered your demand, or that the system is oversized and the demand's been lowered over the years. One other impact is the reduced output power from steam turbines. This photo is a steam turbine driven boiler feed water pump. So as you can imagine, if this is taking high pressure steam to generate that shaft power for the pump, if you now have lower pressure, you have less power available. So that's another engineering analysis that has to be done if your system does have steam driven turbines on the high pressure system. All right, now on to a case study. So we're at a VA hospital here. The hospital's central energy plant operates 4 Cleaverbrook 600 horsepower dual fuel fire tube boilers. They're firing primarily on natural gas. 110-pound steam is distributed across the campus and reduced to medium and low pressure systems via PRV stations. The plant operates well below capacity, maxing out around 50% of the combined rating of 3 of the 4 boilers. So assuming that 1 boiler is available as a standby, the system was originally designed for 3 boilers operating. No end users require high pressure steam directly, which simplifies the potential reduction in boiler operating pressure. And SMI conducted a feasibility study using 80-pound steam as a target. The conclusions from the study were SMI performed the study in accordance with the DOE best practices and determined the following. The boiler carryover, the boiler outlet nozzle sizing and exit velocity limits were found acceptable at 80 pounds without carryover concerns. Steam piping, where calculated velocity increase was about 30%, which remained below velocity limits, again, because they're were well below the system capacity. The PRV capacities, all 16 PRVs were determined to be adequate at the reduced inlet pressure, as well as once we evaluated the new pressure drop through the system. Steam meters remained within the manufacturer specified velocity range and will be recalibrated. The feed water pumps, there was 5 15 horsepower inline centrifugal pumps with VFDs evaluated to be capable of maintaining flow and net positive suction head margin at reduced discharge pressure. The steam traps, we conducted a thorough survey and test of the steam trap population, which we were able to use the data from that to evaluate the capacity of the traps, any lift required, and it was determined that was all going to still be sufficient. So our overall conclusion was that all systems should maintain adequate capacity and performance at 80-pound operation. We also evaluated all the savings impacts pretty much down the line from what we talked about earlier, and found that approximately 1% of total annual fuel use would be conserved by reducing pressure. And you can see here each of these was evaluated and quantified. The key conclusions here: the boiler operation at 80 pounds is technically feasible and presents no operational concerns. Efficiency improvements achieved primarily through reduced losses in combustion, thermal losses, steam leakage and trap losses, blowdown energy reduction, and blowdown energy reduction. The fuel savings fall below the DOE's 2 to 8% average range due to an absence of high pressure steam users. Although that did simplify the evaluation, that would potentially save a lot of energy if there were high pressure end users. They have a modern, well insulated system. It's also a short high distribution loop, so they have shorter runs. It is well insulated. They have a minimal number of traps, and so there's just less to save there, but still good savings for the measure, just below that average range. They also have a modest enthalpy change. So this, as you can imagine, this measure, the results are increased by being able to reduce the pressure more. We're going from 110 to 80. Often you're looking at systems and you're talking about going from 200 to 100, and then the savings are more significant. So 30 pounds is not a significant amount of pressure, although the savings are still fairly significant, just not in the average range. Recommendations: so target the proposed 80 psi operating pressure, proceed with pressure tests, recommission flow meters and collect baseline data for verification, and conduct post-implementation performance review to confirm realized savings. Now we'll just talk about some best practices and recommendations. I guess first note that pressure reduction isn't just a set point change, it's an engineered strategy. So you're going to want to consult experts. This is probably the biggest cost here is the feasibility study of it. The actual change, unless there's equipment replacements required to accommodate the change, the actual change is just changing the set point of the boiler. And so, but you are going to want to consult the experts and have them document average and peak steam loads, verify piping sizes, insulation, trap conditions, PRV capacities, review historical issues like leaks or carryover or water hammer, um, consult boiler manufacturers to check nozzle sizings and boiler performance at lower pressures, evaluate the feed water pumps, flow meters, steam traps, and PRV performance at lower pressure, and evaluate impact on pressure drop and steam velocity. You also want to test before doing the permanent change. So it's recommended to do like a short-term test where you're dropping the boiler pressure in 10 to 20 pound increments. You monitor system conditions, observe for any problems like water hammer or wet steam, and then go from there and confirm that that everything's okay and that you should be able to continue at that lower pressure operating point. Some other recommendations. You want to fix the basics first. So you want to fix your trap failures, your leaks, your insulation gaps, water chemistry, which can lead to carryover, as we mentioned, any blowdown issues. I mean, if you are having any issues with carryover, with water hammer, a lot of these measures, fixing these things will mitigate those problems, and then you can proceed with trying pressure reduction. But if you're already having some of these issues, like water hammer or poor water chemistry or blowdown, you may exacerbate the problem by lowering pressure. Now, you will mitigate losses through trap failures and leaks and insulation, poor insulation, but but still, you would want to address those problems anyway. You want to pair with monitoring tools. So you want to install new or recommission and calibrate existing steam meters so you can see the impacts. You're going to want to, that'll also help you if you are not hitting set point in any of your buildings to see what the demand of that building is and what the impact on the pressure reduction is. You're also going to want to trend that data and and validate load distribution, like I was saying. Also consider system. So one of the concerns here is your steam trap performance. A steam trap monitoring system can track that performance over time and kind of show you problematic trends. Instead of just the data in there is pretty interesting. Instead of just noting when a trap has completely failed, you can see the cycles. You can see the cycles increasing over time, or whatever the case may be, and maybe get a better idea of why that trap is failing, if it's overloaded, if it's a poor application, or if it's just maybe you start to lose faith in that manufacturer, or whatever the case may be. But it gives you more insight. You should also consider system parameters. So as we just showed in our case study, not all facilities see the same savings. The best results are going to be when the boilers are oversized, if there's long high pressure distribution runs, if there's a lot of traps, and especially if they're paired with a high failure rate or poor trap maintenance history, if there's poor insulation coverage, if there's frequent steam leaks, high fuel costs, which basically will, increase the value of any system savings, low boiler efficiency along the same lines. If it's continuous operations, so a lot of run hours, then obviously that's going to increase your savings. Also, if there's poor condensate return, that basically contributes to a low system efficiency, and then any steam conserved has that much more impact on your bottom line. There's a lower benefit when there's short, efficient HP runs. If there's minimal pressure reduction across PRVs, so like if you have an 80-pound system and you have PRV stations that are dropping down to 60 pounds, you probably don't have a lot of room to drop your high pressure side pressure, because you can't operate the PRV, say, at 70 pounds upstream and 60 pounds downstream. So if there's a lot more room there to reduce that pressure, then you're going to have a better benefit. If there's not, then you have a lower benefit. If it's a well insulated new system, efficient distribution system, you're going to have a lower benefit because there's just less losses. And that is the end. So I want to thank you guys all for joining. I'm going to stick around for a bit for any questions. As Ashley mentioned, we do offer PDH certificates for attending. The procedure for that is to email me at cbean@steammgt.com, and we'll provide that for you. And also, we have a really exciting guest on our next showcase webinar. That's where we have a guest speaker and a guest presenter. That's going to be on December 9th. And we have Tim Unruh from NASCO, which is a National Association of Energy Service Companies. He's very knowledgeable, expert in our field, and he's going to be talking about energy savings performance contracts, and giving some background on those and emerging opportunities there. And so we're really excited about that. We think it's going to be a really good one. So we encourage you to go ahead and register. You can register with the QR code right there on the screen, right here. There's this QR code is if you are interested in scheduling a technical presentation for your team. We do a lot of these types of presentation for, engineers and development teams to kind of get some ideas stirring about different opportunities that can be found in for efficiency in STEAM systems. So yeah, so please do that if you're interested. Otherwise, we just thank you so much for joining us. We're glad to have you. We hope you have found this valuable and informative, and I will hang around for any questions. Actually, also just noted that we are exhibiting at the NASCO R3 conference in Vegas at the beginning of November. So we're going to be at booth 311. If you are going to be there, please stop by and say hello. Yeah, and feel free to drop any questions. I think I see one. So I got a question here. I'm guessing with the sensitivities of the steam system components combined with the need to avoid double dipping on potential energy savings, that the method used to model the plant is very important. Is this all modeled in the SMI custom spreadsheets or any plant software or other? That is a great question. There is different tools for that. Like the DOE has a tool called Measure where you can model a seam system out. Our method is to use to build out a heat and mass balance in our own customized spreadsheets. We also calculate certain aspects separately and then incorporate those back into the heat and mass balance and see how that tweaks the numbers. So yeah, there's different tools available for that, but we have our own tools that we use, custom spreadsheets. Yeah. So yeah, great question. Yeah, I really enjoy that. That's a fun exercise, honestly, building a system out and seeing, where the energies go and how you can impact that, and run in different cases and stuff. It's a fun calculation to do. I actually, if you go to our webinar series page, I believe it's in the industrial assessments webinar. The second half of that is basically instruction on how I build out a heat and mass balance. So if you're interested in that, that's a very good resource for that.